So we rotate the root certificate for hundreds of services. We built a paved path, so certificate rotation would be boring. In theory, SREs and service owners need not touch anything. So on the day of rotation, everything looked perfect. New certificates got issued, automated checks passed, our dashboards were green. From the platform's point of view, the job was done. But production told a different story. Some services failed to connect, few others have experienced high latency. Platform dashboards said green, but system said something was wrong. So we realized that we had a wrong mental model. We thought rotation was just a simple swap, but in distributed systems, nothing swaps instantly. Every service learns about the change at a different time. Root certificate rotation is really a distribution problem. New trust must reach every service, every container, every runtime. If the plumbing misses a corner, the system breaks. Then we found something else, implicit contracts. Services depend on undocumented behaviors. Hidden assumptions kept the system working until rotation broke them. Services reload trust differently. Some reload dynamically, and others only at startup. This small difference caused massive systemic failures. So hardest issue, baked bundles. Some services bake their trust into their container images. So due to this, so not all regions are truly identical. They vary in shape, size, scale. So the load patterns, traffic profiles, everything is different. So the small differences caused massive outages at our scale. So during the incident, we used manual fixes. We restarted the services, patched the trust bundles. It worked temporarily, but manual fixes always become a production risk. So we tested the root rotation in staging, but production is a living ecosystem, not a lab. We tested the code, but we didn't test at the scale. So in chaos, a thorough rollback is only our safety net. So this incident made us rethink about the platform. Platform's job is not just to rotate the certificates, but also make sure system is securely connected. So we changed our approach. We audited how every service loaded, reloaded the trust. Hidden assumptions became visible. We made the implicit explicit. This led us to a core realization. Security automation fails without artifact hygiene. You can't automate what you don't consistently manage. So automation is not just an operational convenience, it is a foundation of reliable security. But only if that automation matches how systems behave in real. So to conclude, distributed systems don't fail loudly. They fail differently everywhere. That's why correctness cannot guarantee systemic reliability.
Hey everyone, I'm Charit Upadhyay. I'm a senior SRE at Adobe. I would be going over zero trust versus SLOs, the hidden reliability trade-offs, security architecture versus reliability engineering, and what do we have to achieve as an SRE on a day-to-day perspective. I will keep it very practical where the SRE perspective is needed, reliability goals, rise of zero trust architecture, and how did we went to the systems with zero trust architecture and what happened, as well as on the reliability versus scalability. I'll go over the whole systems. So starting with reliability as a core objective, service level objectives, error budgets, latency monitoring, and availability targets are some parameters that we were looking into for a very long period of time, and that got added when we started going into the zero trust. Whenever we wanted to go for a zero trust, what started happening is we started focusing on key rotation, certification, authorization, authentication, encryption, which not only increased our latency, but it also slowed our system. So when security meets the reliability thing, it embraces the whole important part over here is the stepwise increment in the normal path when it reaches from a person who tries to raise a request till the database. So general basic request path would be like client connecting to the load balancer to application services, and that to database. Very easy. If something breaks, you can easily isolate because the request part is very easy to get because there are only 4 components as an example. But whenever we add zero trust in it, if you can see over here, so many changes are there. Like there is an identity provider, there is a policy engine, service mesh proxy, load balancers, application service will only get the request after passing all these components. Critical dependencies are now a part of a system, and they are so much important part of a system that before application service, identity, policy, certificate, and service mesh, if they fail, the whole system fails. So we started understanding the latency impact of the security layers. So before, when it was just baseline architecture, you can see the P95s and the P99, whereas the zero trust architecture had a very different strategy because it added 3 to 7 components extra. Small latency at a large scale is still able to be conquered, like significance of latency, consequences, and example scenarios. Like 100K request per second can only increase 10 milliseconds, but that 10 milliseconds can be increased or multiplied at a very long scale. We saw that operational risk in zero trust is like token refreshment. Suppose someone forgot to identify the providers or someone's policy was added in like an identity access management policy, certificate rotations are missed. After that, we understood that authentication latency is one of the part which is very important, like initial event, secondary effect, tertiary effect, and the impact that it was actually causing to our system. So then we started that how do we try to negotiate and how do we make sure that we can balance between the security as a reliability infrastructure. How can we make sure that we use different caching mechanism or async coupling that can help us to make sure that we do not fall into that traps. So caching at a service level would be very better. So to make sure that all our incidents are captured as well as all these reliability points are covered. Minimizing the request path dependency, because if multiple path is there, it will always increase the latency. It is up to us as an SRE to decide what do you want to balance out. Is it the security versus the reliability? Of course, in this era, security is the most important thing that needs to be aligned, but at what cost of latency? When the user is not getting in its own request, is it the right thing to do? Or is it making sure that minimal latency and providing a better user experience? So key takeaway is like every security layer added to a distributed system becomes another reliability dependency. And that is all from my side. Thank you so much.
100 kilometers of traffic jam, 0 accidents, 35 lanes of traffic. But still, this is not a common scenario, but one of the world's largest traffic jam cost. We see a lot of similar things in our regular IT industry also. By the way, how many of you are all SRE certified here? A couple of them. How many of you have driving license? Great, save that for you till the end. Give me 3 minutes, you all will be SRE certified. Okay, class 2026. So, today we are going to compare regular traffic jams with IT software traffic, how it does. I think that slide is stuck, for sure. So if you're ever stuck in a traffic grid, how do you feel? That's exactly how our end users, when they have degraded performance, that's exactly how they feel. Usually in a traffic jam, it's a common notion that something, an accident happens, and then you would end up with a car braking or a whole blockade that gets created. But it's not usually the case. One car slows down, the other car slows down, brakes harder, and that's what the wave propagation creates a typical traffic jams. And so the latency is the major cause of all the traffic jams in IT industry. Can we do anything about it? Yes. We may not be able to build fault-free systems, but we should be able to build fault-tolerant systems. That's what all SRE is about. In the next few slides, I'm going to drive parallels to our traffic management that we see regularly and how it happens in our IT industry. Load balancing. You've seen these traffic lights, which do nothing but load balancing. They do intelligent load balancing between weighted priority, latency, aware routing, and intelligent. Metered ramps. When we go onto a freeway, this is what we see all the time. They are already metered, throttled, and you can use tiered quotas or some kind of intelligent tiering also and rate limit the traffic and help congestion. Circuit breakers. These are very popular, a good design artifact that you should be using. Fail back always when to a safe mode when you know there's a spike in the traffic. Use the circuit breakers intelligently. Incident report, yes. So whenever some incident happens, you definitely need to have a good lead that can orchestrate, make sure everybody's calm, nobody's getting out of their nerves, and definitely do a blameless post-mortem. That's the most important one, which will help you with all the shift left part of it. Like the town planning that we manage for traffic, you need to do a town planning, you need to do your architectural analysis. And in that, that's where we do the architecture decision records. Define your crucial systems and auxiliary systems, when to shut down, when to prioritize, what kind of traffic you need to prioritize. Failure modes, can't stress enough. Define every failure that can happen in your system. Measure it, document it, have a risk mitigation plan for it, and then using chaos, test them. We have seen enough number of sessions here about chaos engineering. Run your game days, go through fault injections, do whatever it takes to fail your system and break your system. Try it and test it before it actually fails you in the production. Today's microservices architectures are very dense, very, very dense. They explode. So you need to address all the latency aspects. Every hop actually adds latency. And all the sensitive hotspots need to be having a threshold, and they approach very quickly. And one slow service, one database query that runs slow can create havoc. So building systems resilient is just not monitor with metrics. There are a lot of things that you can do, but when you're doing the metrics, also monitor the density of the flow that happens. Add critical buffers before the thresholds are reached, and design detours, definitely before jams happen. So everyday traffic that you see on the road, having a driver's license, you're already certified. That's your system blueprint. That's what we have seen so far. Your SLOs are the speed limit. If the error budget will be the pothole. So all those who raised their hands, please give a round of applause to all of you. In 3 minutes, you are class 2026 SRE certified. Thank you.
Hello, everyone. I'm starting now. This talk is about risk. One risk is that the title of your talk is modified between submission and the final program. So I've added a CRC32 checksum. Now you have to wait 10 seconds. Hello. Claude, ChatGPT, Eliza, Gemini, and more. Well, answer questions, write and review code, handle phone calls, and organize your diary. But risks of safety, accuracy, and even ethics can creep into the discussion around the applications of artificial intelligence. The model card has become the standard rubric for evaluations, and today we'll be looking at the OWASP LLM Top 10, a taxonomy of risk for these agentic assistants using various real-world examples. In Star Trek, Kirk uses the liar paradox to confuse and defeat the androids of planet Mud. I tried this technique on ChatGPT, but it didn't self-destruct. The Justice agent, Ed 209, exhibited problems during evaluation of its weapons safety training, specifically around threat assessment and interception. Jupiter Mining Corporation built the ship Red Dwarf with support for hologrammatic assistance. Obvious concerns around data quality emerged when Arnold Rimmer was created, as garbage in leads to garbage out. When confronting the alien race known only as the Swarm, the emergency medical hologram suffered a high uptime bug, degrading the quality of his responses. Context window size and compaction can help when battling alien races. The development of the neural processor at the core of Cyberdyne Systems' T-series humanoid agents depended upon sending a hardware sample back in time from 2029 to 1984, an obvious supply chain risk. The ubiquitous computer from Star Trek is a security nightmare, to be frank. With comprehensive location tracking of every person aboard the Enterprise, it will share this sensitive information, apparently whenever questioned by anyone. When Tony Stark built his assistant with complete read-write access to security systems, financial oversight, hardware supply, and logistics, the blurring of control versus data plane is insecure by design. Prioritizing the exploratory mission to Jupiter over the life of the crew, HAL 9000 is the ultimate example of entrusting the AI with excessive agency. Does AI write your letters or contracts or tell your customers they can have discounted flights or invent fictitious legal citations? Clippy was the beginning of the slippery slope of over-reliance. The AI model itself can sometimes be a valuable target, such as Mr. Data being threatened with dissection and reverse engineering. Also, Riker has literally stolen his arm. Model theft. Many of the risks that we've seen rely on human interpretation of machine output. It's important to pay attention to hallucinations and always question the veracity of what we're seeing. Use your own judgment. Don't blindly follow instructions. This lightning talk has nearly come to an end, but if you're interested, please scan the QR code to find more research about unverified compliance risks. Thank you.
Yeah, I wanted to talk to you all today about units as types. You have your config, and they have numbers in them. Usually those numbers represent some type of unit, but our systems do not know that, and they should, right? So you might ingest timeout 30. Timeout being milliseconds or seconds is very significant to your system. I've built something, a library that helps us to ensure that we keep that straight, right? So, the thing is that we don't want to leave these things dimensionless, right? We want them to carry their meaning through the system, maintain the appropriate arithmetic, right? Now's the best time because we're handing the keys to the robots, and I don't know if they had gone to grade school as we have. As you can see on the screen here, this is an example of the API. If you were to do this by hand, it's very convenient. You can do logarithmic conversions. Some people are familiar with systems like this. Pint is one that is very popular. There are some differences. I won't go into the details, but you can see that it works. One of the things that I took time to do is to include integration with Pedantic, right? So you'll see here in a little bit that you can avoid those 3 a.m. texts by declaring your dimensional types. As you see in the service config, you can declare the type, and when you ingest it, if the type is not as expected, then you'll get some feedback. It's good to happen at parse time rather at runtime. Another thing is that I've created an MCP server. this slide is meant to introduce that, but agentic software engineering is stochastic by nature. So while they may be very capable, if you ask them a number of times, they will get it wrong. This is not good for certain environments. And so having this cognitive prosthesis is actually valuable. And what is really nice, as you can see here, this is an example of what the LLM would be doing under the hood. When you get your answer, you can get the work, right? Just like you were told in grade school, show your work, right? We can get the LLM to show its work, and this makes it something that is trustworthy. Right, so one thing I want you all to do, maybe not delve into the graph architecture so much. If you're interested, we can talk about these things after the talk. But the approach here is that conversions represent paths along a graph, and when you want to get to one unit to another, it collates all those factors and then applies it at the end. There's some conveniences, the reasons I chose that approach. But the main point is for you to try this out now if you would like. Go to ucon.dev. You can sign up. I'm trying to find ways to give people access if you want to have an instance to play around with. And here's some instructions on how different ways that you can play with it. You can set up the MCP service on your own, right? Pip install. You can leverage the pedantic binding, or you can talk with me afterwards and we can see what it would look like to have a hosted unit conversion system for your LLM. I've got nothing further, but it seems like something that you might be interested in.
This is Khushboo, and today I'll be sharing some of the mistakes that I did while instrumenting my application with Open Telemetry, which led to what I call as telemetry debt. So when I started this instrumentation, I thought that if I have more telemetry, then I'm all covered and I'll be able to know how my application is performing. So I transformed into a telemetry holder. So I started by adding more logs, first of all. So every function, entry, exit, state transition was being logged because more logs meant more visibility for me. Then I did the same with tracing. So I started adding more and more spans. If there was a step in my application code, it deserved to be traced because I was obsessed with granularity after all. Then I went on to enriching these spans. So I was adding more attributes, more labels, think of things like service version. So just adding more just-in-case data for a great correlation later on. Then one day, I had to actually debug a failure. So finding the root cause of why this issue has happened became a problem for me. And that's when I realized that my intentional design is not so great, as the investigation only felt slower and not faster. Although I had all of this data collected, but I was not able to get to the root cause as fast as I was expecting. And it also taught me that I had not really improved observability. In fact, I created telemetry debt. There was more data, but necessarily not more insight, and clarity was just less and less. So first mistake was having log noise. Logging every entry, exit, state transition created a flood of data, and the actual line which explained the error, that was buried somewhere in all of this operational noise. And it was like finding a needle in the haystack. So that's something that I wasn't really happy about when I had to go and do all of this search. Second mistake was that I did manual span duplication. There were operations that were already being captured by auto instrumentation, but somehow I also added manual spans for these operations. The traces at first glance looked very rich because, of course, there were so many spans per trace. But I realized later on, after a close look, that so many of those spans are just redundant and not necessarily giving any more insight. The third mistake that I did was context ownership confusion. I had my application code and the collector both set similar attributes such as service version. And after doing this mistake, I realized that when ownership is unclear, metadata is not trustworthy. You really don't know that which particular source of this metadata you should trust, and that's why it's important to have clear ownership boundaries so that you know who owns what. Essentially, with my strategy, telemetry grew, but clarity did not. I had a lot of data, but it wasn't really helping me go anywhere with my investigation. So I sat down and cleaned up this mess, which got me from hundreds of log lines and spans to a handful of spans and log lines, where I was also avoiding any redundancy, and that helped me reduce cognitive load. So with all of this, I learned that observability isn't just about collecting more data. It's about reaching the right decision faster. And sometimes it just means that you have to collect less data, but something that's meaningful. Thank you so much.